Okay. So today we have exciting guest, Nicholas Sharp. Nicholas Sharp is a senior research scientist at NVIDIA Toronto AI lab. His research develops new algorithms and representations for processing geometric data robustly and efficiently, with applications to computer graphics and vision and geometric machine learning/deep learning. He received his PhD from Carnegie Mellon University, advised by Professor Keenan Crane, and was a postdoc at the University of Toronto with Professor Alec Jacobson. And he was affiliated with Fields Institute for Mathematics and Vector Institute for AI. Nick's work has been recognized with Best Paper Awards, SIGGRAPH and SGP, including this year SIGGRAPH Best Paper Award, Software Award, SGP, and NSF Graduate Research Fellowship, and Fields Institute Postdoctoral Fellowship. He also happily leads several open source software libraries and projects for 3D computing, including Polyscope and Geometry Central. So please welcome Dr. Nicholas Sharp. Yeah.
Awesome. Can you all hear me okay? All right, great. So thank you so much for having me here to speak with you all today. I'm really excited to give this talk and also to have some opportunities to talk with some of you afterwards. And thank you so much for the kind introduction and all of the organizational details that you all take care of. So to tell you a little bit more about my area of expertise and where I'm coming from. So I work in 3D geometry, computer graphics, and machine learning. So this is split over both traditional geometric algorithms and data structures. So things like how do we leverage differential geometry to derive new algorithms for computing on surfaces, PDE-based formulations, finite elements, simulations, and designing the data structures and the numerical algorithms that make these tools robust, efficient, and easy to use. And then also more recently, a really big and important class of techniques in this space is how to solve machine learning problems in the context of 3D geometry. So this is things like how do we integrate 3D data as inputs and outputs to our problems? How do we work with 3D representations as sort of intermediate stages of our learning pipelines? And also what are the right architectures and numerical techniques for performing machine learning on 3D data? Fortunately, working in 3D is an area where the applications and the impacts are fairly easy to imagine. So these days, there's all kinds of 3D data that's really important to the world around us and to things we want to do. This ranges from 3D scans to technical data and scientific data, applications in computer graphics and AR experiences, all kinds of things we want to manipulate. And then there's a bunch of tasks we want to do with all of that data. We want to emulate and simulate it. We want to synthesize new examples of this kind of data. And along the way, we need a whole bunch of geometry processing and machine learning to map all of these data onto these applications. So these range from things like shape priors to deformation methods to all kinds of processing and learning tasks. So when I talk about geometry processing and when I talk about 3D machine learning, I'm talking about all kinds of algorithms for manipulating all of this 3D data and mapping it onto these kinds of tasks that are general, they're simple, and they have to be robust because robustness is a huge and kind of destructive challenge in this space, as well as being efficient and offering new capabilities. And working on machine learning in the context of 3D is really, really interesting for a couple of reasons. One that's very near and dear to my heart is that anytime we're working with 3D surfaces, we have a lot of connections to classical differential geometry, and we can build up our algorithms in terms of this language of 3D differential geometry. And this gives us a really rich base of both theory and computational techniques to build on. But a little bit more on the practical side, machine learning is very often driven by and shaped by the data we have available. And we're really living right now in a golden age of 3D data, because only in the past 5 years or so, for the first time, has it really become true that we have large, where large here means more than 100 data sets of 3D objects that and sort of 3D representations that are available to us for learning problems. And this is really exciting because it's really transforming geometry processing and computer graphics and vision in a very deep way. One of the big transitions that's happening is that we're moving from manual to automatic techniques for a lot of these problems. And to give an example of that, a lot of the geometry algorithms we've built up, for instance, in computer graphics over the past 30 years are really algorithms that were meant to be driven by a human. So when you're coming up with these algorithms, you're imagining that there was some skilled technical artist sitting at a computer, intelligently manipulating some software and driving your algorithm. And in doing so, they would, deform a character or generate some 3D shape or something like that. And we really sort of invented these algorithms with the intent that they would be driven by a human. But now that we have these massive data sets of 3D data, we want to process them offline and automatically and with machine learning, we now need to take this whole algorithmic stack, drive it fully automatically, and even worse, we want to differentiate through it. So this is sort of forcing us to reinvent our entire stack of representations in geometric graphics and vision to find the new techniques that are amenable to these kinds of problems. So all of this is to say that 3D learning is really exciting right now, and it's really, really unsolved because I don't know, for almost any classic task in graphics and vision, it's still an open question for how to map it into this new world of big data and learned representations. And this point of representations is really important because kind of the classic story of 3D geometry and graphics and vision is one of how do we represent our 3D objects? Because even though 3D objects are really easy to think about, there are many, many possible ways to represent them with computers that have a lot of different trade-offs involved. So to give some examples of these, if we wanted to represent this 3D shape like a bunny, we might use a point cloud, which is just a collection of points in 3D space. We might represent it as a binary voxel grid, kind of a Minecraft-y looking surface. We could represent it as a tetrahedral mesh, which decomposes space into a non-overlapping set of convex tetrahedra. We could make it a triangle mesh, which is probably the most widely used representation in things like video games and displays and AR today. And there are even many more options beyond this that I haven't shown here, things like subdivision surfaces or constructive solid geometry trees or implicit representations. And all of these different representations have different trade-offs in terms of how much storage they take, how high fidelity are they, and what algorithms or tasks are easy or hard on that particular representation. So no one of these are best, and we have sort of a constantly swirling set of trade-offs in terms of different representations coming in and out of style, discovering new data structures and accelerations that we can build on top of these. And that's all just in traditional vision and graphics. Now, as we're trying to learn on these representations, well, machine learning is also very much about finding the right representation, whether that means, engineering features or choosing the right intermediate architectures in your network. One way or another, it's really important to find the representation on which you can learn effectively. So all of these challenges now take on this extra dimension of which representation is going to fit best with the learning task we want to perform. And the focus of what I want to tell you about today is going to be about a particular class of representations involving neural networks and implicit function representations of surfaces, and some new techniques that we developed to allow you to compute more effectively on this. So we'll sort of break this into three main pieces today. So first, I'll talk more generally about why these neural implicit representations are interesting. Then I'll tell you about a numerical technique called range analysis that we're going to use to manipulate these representations. And lastly, we'll see how this allows us to circle back to these important applications in graphics and vision and build higher level geometric queries. Although I've kind of motivated this with a bunch of high level things you'd want to do in graphics and vision, most of what we're going to talk about today is actually not going to be about any of these high level applications. And instead, we're going to talk about some low level sort of gritty numerical analysis of neural networks that turns out to be the key to unlocking some new techniques in this space. So I think it's pretty fun. Hopefully it's interesting to you all too. And I also think that this should be interesting, even if you don't know or care at all about 3D geometry. We'll just talk about some interesting numerical techniques for neural networks themselves. But let's start about these geometric representations with neural implicit functions. So what am I even talking about? So we said there are many different ways to represent a shape. And the idea of an implicit function representation of a shape is to just say, I have some function, which takes as input a 3D coordinate and outputs a real number. And then we'll define our shape as being the set of points where that function evaluates to 0. So in particular, by convention, we usually say that any place this function evaluates negative, we're inside the shape, and any place the function evaluates positive, we're outside the shape. And this representation goes back 40 years. People have been explicitly writing down functions by hand, these crazy trees of algebraic computational expressions, in order to define surfaces. And this has led to some really interesting techniques in computer graphics in the past. But lately, it's become particularly interesting because of the possibility of making this function not a handwritten function, but rather having our implicit function be fitted as a neural network or some MLP, which again takes as input spatial coordinates and outputs a scalar value defining the surface. So then we can take this representation and fit it to data or generate it or play all the games we want to play with it. And for any sort of choice of weights or choice of outputs of this network, we have a corresponding 3D shape given in space. So these representations are really exciting in computer graphics and vision for a couple reasons. One of which is that they work remarkably well. So the shape on the left here is a rib cage that I started with some known data. I had a surface mesh of this rib cage, and I fitted a multi-layer perceptron to be an implicit function, which again encodes this shape in the way I described previously. And you might think it takes millions of weights or something like that to encode the shape, but it actually doesn't. It turns out here just about 7,000 weights are enough to get a quite nice looking representation of this rib cage. So that's already really exciting. And it also easily generalizes to other things we'd want to do with data. So on the right, there's a 3D animation of a galloping horse. So all I did was I took this implicit MLP and I added one extra input, which is a latent parameter corresponding to time. So then as you sweep this time parameter forward, you get a sequence of implicit functions parameterized over this latent space where the latent dimension is really just time. And corresponds to a whole animated sequence of galloping horses. And we got that totally for free just by adding one more input to our implicit representation. This has led to a bit of a revolution in computer graphics and vision in the past 2 years, where many different problems have been sort of ported to this implicit representation. Sometimes this is exactly implicit surfaces, like I've talked about here. And some of these cases are sort of more general so-called neural fields, where we take the paradigm even more generally, and we say we take some data that's represented on some spatial domain, so an image or volumetric data, or who knows what, and we parameterize that data via a neural network that takes as input a point on the domain and outputs the value on this domain. When you might have seen this picture of this yellow Lego bulldozer, or these NERF models, which have really blown up in computer vision. And here the geometry, it's slightly different. It's not a inside-outside function. You use a density function where the neural network tells you is space very empty here or very dense here, but it's essentially the same idea, and pretty much everything I'm talking about still applies in that case. So these have become extremely popular, and I think it's worth talking for a minute about just why this is. Why did this blow up so much? Why are we making so much progress so fast with these representations? And this is a little bit my opinion, but to me, the reason why this has worked so well is because we have all of these different representations we might use in computer vision and graphics to work with 3D geometry. And then we also have a whole bunch of tasks we'd want to do with these representations. So these are things like 3D reconstruction, where you have some observed data, like images of a scene or output from a scanner, and you want to recover the base geometry. You have compression, where you want to concisely represent your geometric data, or inverse design, say, find the shape of a bracket that does a good job supporting this load, and many other geometric problems. And because we have this giant cross product of all of these representations and all of these tasks, well, we've had to invent a lot of really complicated algorithms to map all of these representations onto all of these tasks. So for instance, if you want to do inverse design with a triangle mesh representation of a surface, well, you need to have your objective function. But if you just naively optimize a triangle mesh, what will happen is it'll tangle up and you'll get crazy spaghetti as output, and that's not useful. So instead, we build remeshing routines. Oh, but also gradient descent is too local to work with a triangle mesh. So we need a hierarchical solver, and then we need a multi-stage optimization process because it's non-convex, and we need to split into a sequence of convex problems. And it goes on and on and on. And we've been successful. We've built up some amazing tools this way. But these tools are quite complicated and very particular to the particular sort of cross product of, or combination of, representation and task. Whereas when we reformulate a lot of these tasks using this neural implicit representation for our shape, the algorithm that we run is pretty much always just gradient-based descent on the weights describing our neural network. So we're just doing some kind of gradient-based descent on this neural implicit representation. And then all of these different tasks basically just come down to writing down a different loss function and doing that gradient descent on that loss function instead. And if we want to combine two of these tasks together, well, we just add our two loss functions together and we do gradient descent on that. Maybe that's a little bit of a rosy view of how this all works. Sometimes it's a little harder than that, but at the end of the day, it's a lot simpler and it's a lot more universal, and it really cuts through a lot of the complexity that we had otherwise built up with these representations. Another thing that's interesting about this class of applications is that we tend to call this machine learning because we're using neural networks. They're neural implicit surfaces. Of course, it's machine learning. But actually, for a lot of these applications, there is no data set. There's no statistics going on that we're trying to fit to. We're really just saying, I have one example. I'm using my neural network as a function space to represent the solution to that example, and I'm doing descent on the function space. So people say, I don't like this term actually, but people call this overfitting to a single example. So we're not even thinking about generalization. There's no notion of training and testing or anything like that. We're just optimizing our representation to fit as well as possible to a single example. For some of these, we also map this into more traditional learning settings where we have a population and we're trying to generalize or something like that. But very often these tasks right now are being leveraged even just in this overfit to a single example routine. So here, neural networks are really just interesting to us as an effective function space to parameterize these problems. So as I said before, the benefit of this neural implicit representation is that it's general. You just need your loss function. It also ends up having adaptive complexity. And what I mean by that is that a challenge of surfaces is that you often don't know ahead of time where your geometric detail is. So for instance, images are great. They're always just a grid of pixels. If you want a high resolution image, you just use a bigger grid. Nothing really changed. Surfaces are a lot harder because often you have adaptive detail and unstructured representations in different regions of space. But using this neural implicit representation, we don't have to worry about it. We can, much like images, just use a bigger neural network and we get more resolution. And that resolution will roughly end up where it needs to be in the implicit representation. Here's a quick preview of this. Hopefully my video comes through okay over Zoom here. We'll talk more about this application at the very end. This is just to show an example of some of the cool things you can do with these representations. So here's a reconstruction problem where the input is a collection of, in this case, synthetic renderings of a 3D object, and the output we're seeking is a reconstruction of the underlying object. And all we're doing here is just basically gradient descent on their rendered images to match the images we got as input. And this is amazing because we don't have to deal with all of the challenges we would have to deal with if we wrote this down the same optimization problem on a triangle mesh. On a neural implicit representation, it's just gradient descent. As I mentioned before, when we do want to circle back and work with the ML pipelines, we want to do latent interpolation or we want to do generative modeling, we're also in a really good position to do these kinds of tasks when our representation is already just a neural network. There are some downsides, though. It's not everything is good. One really big downside is that these representations are very, very computationally inefficient because it's not that we evaluate our network once and it spits out a whole shape. We need to evaluate this network potentially millions and millions of times in order to interrogate the underlying shape. So if you just want to say render an image of one of these surfaces represented with a neural implicit representation, it might require 1000x more computation than rendering the same image with a triangle mesh. So there's a lot of research in trying to make these more efficient, but even in the best case, we're still paying many orders of magnitude of computational complexity here. And perhaps a more fundamental issue is that although it's very easy to fit these representations, again, we can solve a lot of these problems and spit out the surface we care about via gradient descent. It's not so easy to formulate other kinds of applications on top of this representation. And that's actually going to be the main challenge that we talk about and that we offer a solution to today. So if we come back to this picture, suppose I have a shape that's represented as one of these neural implicit surfaces. The question we want to ask is, how do I do geometric queries on this shape? So the most basic one you can imagine is casting a ray in space and testing where it intersects the shape. Or maybe say I've given you two of these shapes represented as these neural implicit functions, and I just want to know whether they overlap each other in space at any point or not. This is a really basic query you need if you want to say, drive a robot or do a simulation in a space where the shapes are represented as implicit surfaces. We certainly need to be able to test when we're colliding and when we're overlapping, but it's not obvious at all how to take one of these implicit representations and evaluate this query. So the way that people have tackled this in the past is with a formulation called sign distance functions. And this is not what we're going to talk about today. I'm just telling you about the alternative solution and why it's not sufficient. But to hear about this alternative solution real quick. So the idea of a sign distance function is we take our implicit function and say, not only does its sign tell you when we're inside or outside the surface, but furthermore, we're going to ask that the magnitude of that function give the distance to the surface, or maybe just a lower bound on the distance to the surface. And this is equivalent to saying we have a Lipschitz bound on the gradient of our function. And if you do have one of these sign distance functions or bounded Lipschitz functions, then we can actually use it to do a lot of these geometric queries. So to give an example of that, the classic example is what's called sphere marching. So in sphere marching, again, we have some shape represented as a neural implicit function where this function f is some neural network applied to 3D coordinates. And we want to cast this ray. So we have some point and direction of interest, and we want to find where the ray, this dotted line, intersects the surface. And this is a really basic low-level operation you need all over the place in graphics and vision. Well, if we know that our function is a sign distance function, then what we can do is we can look at the magnitude of our implicit function at this source point, and it gives us this sphere that we know must not contain the surface. So then we step forward to the place where the ray exits the sphere, and then we repeat. If we again look at the magnitude of the function, because it's a sign distance function or it has some Lipschitz bound, it gives us the sphere that we know must not contain the surface. So we step forward again, and we repeat the stepping forward process until either we diverge and we miss the surface, or we converge extremely close to some point on the surface. But again, the really important property is that you could only do this sphere marching. It's only a valid algorithm if you know that you have a sign distance function or this Lipschitz bound. And if you're going to think of it in terms of a bound, it needs to be a reasonably tight bound, or else this is going to be an extremely inefficient operation. But so these sign distance functions are great, and they've had a lot of success in other areas of geometry. But I want to argue that they're really not a great solution in this neural setting when we're working with neural implicit functions. And there's a couple reasons for that. The most basic one is just a robustness challenge, that there's not really any known easy way to guarantee for sure that our networks have this sign distance function property. So instead, we end up with it only as a penalty, as an approximate sign distance function. And this means that the property doesn't hold everywhere. And thus, in some places, it fails, and our queries fail, and our algorithms fail, and our end applications fail. More fundamentally, if we're asking that our implicit function be a sign distance function, in the best case, this only really holds at the end of training. At the beginning of training or fitting this neural implicit, when we randomly initialize it, this property certainly doesn't hold. So what that means is that if we wanted to use these kind of geometric operations to define our loss functions, we have a problem, because now the query is going to output nonsense when we're randomly initialized at the beginning of training. Also, sometimes we just don't want to model our problem with a sign distance function. One important example is using occupancy functions, where instead the neural network spits something more like an inside-outside function. It's just 1 if you're inside and -1 if you're outside. And this fits much better with, say, optimizing for silhouettes in computer vision. Or another example is these density length functions that NeRFs use. There are a lot of relationships between these representations, but at the end of the day, we buy ourselves a lot of flexibility if we aren't forced to work with sign distance functions. So it'd be really awesome if we had a way to do these kind of geometric queries on 3D shapes represented as neural implicit functions that doesn't depend on them being a sign distance function. So this is sort of the problem statement we want to solve. If I give you a shape represented as a neural implicit surface, I don't tell you anything else about the function. It could be a randomly initialized neural network. How do I do geometric queries like casting rays or testing whether two shapes intersect, or even better, building spatial hierarchies on top of these shapes, which are really important for a lot of algorithms in graphics and vision. If you just think about this as directly from the point of point sampling your neural network, it kind of seems impossible to do this. The best you could do is randomly sample functions in space or add some approximate penalties, and maybe you would get lucky and you would get a decent solution most of the time, but you would certainly not have any guarantee that you certainly get the right answer. So we're going to need to develop some numerical tools that really let us do this sort of computational geometry on these neural implicit representations. And the tool that's going to let us do this is a set of numerical techniques called range analysis. Give me one moment to take a sip of water. All right, so range analysis is a numerical technique that goes back 30 years in the numerical methods literature, which is not specific to neural networks at all. It's a general technique. And the basic idea is to say, I have some function or some computational graph or some numerical procedure that I'm interested in, and I have some bounded range of inputs to that function. And I want to know the bounded range of outputs that that function has over that range of inputs. And this is going to be a numerical technique that computes it automatically. The historical note here is that range analysis was actually developed mainly in the context of floating point arithmetic. So you would say, I have some computational graph and I want to have outer bounds on the amount of floating point error that is incurred by this computation. But in this case, we're not going to mess with that at all. We're not going to talk any more about floating point today. We're just interested in this as a general tool that says, given a range of inputs to a function, find the range of possible outputs to that function. And the most basic and well-known kind of range analysis is called interval arithmetic. So interval arithmetic is one technique to do range analysis. And interval arithmetic is simple enough that we can basically learn it in one slide. It's really beautiful. The basic idea of interval arithmetic is just to say for each scalar in an expression or in a computational graph, we're going to track, instead of just the value of that scalar, we're going to track upper and lower bounds on the value of that scalar over our range of interest. So each value gets actually split and sort of transformed and saying, instead, let's track upper and lower bounds on the value. And then we'll write down some rules to push these bounds forward through our computation. So for instance, if we have some intermediate quantity and we know upper and lower bounds on that quantity and we add a constant to it, well, that just turns into adding a constant to the lower and upper bound. Similarly, you can derive expressions from multiplying a value by a constant or even multiplying two of these values together. Similarly, if we apply some nonlinear function, then we can derive the corresponding update to these upper and lower bounds through some nonlinear function too. So here, the exponential function is really easy because it's monotonic. So if we know bounds on x, the bounds on the value of exponential of x are just the exponential of the bounds. So what's going on here is that this is an automatic function transformation. And if you're familiar with sort of computational techniques in modern machine learning, this is a lot like forward mode auto differentiation. So autodiff takes your function and analyzes it and sort of automatically pushes some extra data forward to compute derivatives of that function about a point. And range analysis is going to take our function, do some automatic arithmetic and push some quantities forward to give us bounds on the function instead. From the standpoint of these neural implicit functions and these 3D geometry queries we want to do, this is really exciting because what this means is that if we take some region of space, which is the input to our neural network, and we analyze it using these techniques, this range analysis can tell us, hey, your function, your neural implicit function, no matter how crazy it is, it's definitely entirely outside the shape in this region, or it's definitely entirely inside the shape in this region. So this is sort of the numerical foothold that lets us start building up higher level queries and operations. This range analysis has been used really widely in graphics, at least in a certain corner of computer graphics, going back to the 90s. And it's actually, I didn't know this originally when we started the project, but there's also a place it shows up in machine learning and neural networks, which is robustness and verification. There's been a couple of really cool papers in robustness and verification that say, if I want to, have some bound on the output of my neural network and a ball around some evaluation point of interest, they've used these interval arithmetic techniques to push forward like certification bounds on the neural network output. But aside from the basic fact that it's using range analysis, the rest of the machinery is very different in that case. But I think it's a cool connection. And by the way, if you're interested in range analysis, more generally, I have at the bottom here the citation to the Stolfi and De Figueiredo textbook, which is a really amazing reference. It's distributed as a PostScript file, which is how you know it contains deep and wonderful truths about mathematics. And I definitely recommend checking it out. Okay, so interval arithmetic, right? It lets us take a bounded range of inputs to our function and gives a range of outputs to the function. Let's see how this lets us do some really basic things like casting rays. So we had this example before where we have a shape of interest and we want to cast this black ray and find where the ray intersects the shape. Before, we took advantage of this SDF property to do sphere marching. Here, we're no longer assuming we have that property. We're in a more general setting. But instead, we'll use range analysis to do interval marching, where we use these bounds to step forward. So what we can do is we can take our array and analyze some region of that array. So here I've drawn this orange little segment along the array. And if this range analysis tells us that that ray is entirely outside the surface we care about, then we can step forward and start again. Now, suppose we try analyzing this region. Maybe our range analysis can't tell us successfully that this region is fully outside the shape, even though it actually is. I'm going to talk more about that in a second. But that's okay. We can just try a smaller region. Sure enough, our range analysis successfully tells us it's outside the shape. So we step forward and we step forward until we eventually converge to a point on the surface. So this basic example of raycasting implicit functions with interval arithmetic is the thing that's been done a fair bit in computer graphics going back to the 90s. And even some more interesting examples recently. There are these things, this platform called Shader Toy and this artist Inigo Quiles who makes some absolutely beautiful 3D illustrations that are generated entirely with manually written down implicit functions. And interval analysis has been used to analyze this kind of data. There's also a game called Dreams for the PlayStation that you might have heard about. I've never played it. I don't actually play many computer games, but the entire engine for that game is built using this technique, which is really interesting. It's also used a bit in computer-aided design and constructive solid geometry. Okay, but all of those are not for neural networks. All of those are just classic functions written down by hand. But neural networks are just a function. If we have a technique for analyzing numerical functions, we can apply it to neural networks. However, something goes wrong. It's not quite that easy. The problem is that the bounds we get out from this interval arithmetic and from range analysis in general, they're guaranteed to be valid bounds in the sense that the bounds always really do contain the output of the function over the region of interest. But the downside is that these bounds are not guaranteed to be tight. They can be extremely loose. And in fact, if we naively take these neural implicit functions and we analyze them using this interval arithmetic, we get bounds like plus minus 10 to the 8, which are technically correct bounds on the output, but they're not actually useful to us. They don't let us effectively do any kinds of queries. And to see why this cancellation happens, we can step through interval arithmetic for a really, really simple function. So our function here is just the function which takes as input x and produces as output 2x minus x. So you may notice that this is actually just the identity function. I've just written it in a silly way. So we're analyzing the identity function right now. And let's suppose we're interested in the identity function over the range of inputs 0 to 1. Well, we know that if we apply the identity function to the range of inputs 0 to 1, we should get a range of outputs over 0 to 1. This is pretty obvious. But what happens if we step through these interval arithmetic computational rules that I showed before? First, we expand out to 2 times our interval minus our interval. We pull in the 2, we add the 2 bounds together. And what we get out is the output range -1 to +2. So this is valid in the sense that it really does contain the outputs of the function in that range, but these are certainly not tight bounds. The reason this happened is because there was some cancellation involved. One of our quantity x was increasing at one point and we subtracted a quantity where it was decreasing, so they should have canceled out, but our intervals don't represent this cancellation, so our bounds become looser. And it turns out that this effect is totally catastrophic on modestly sized neural networks because inside of a linear layer, when you do ax, a times x, there's a huge amount of cancellation happening within the matrix vector multiplication a times x. So these bounds really explode anytime you pass them through a linear layer. So the way that we made this work was to dig a little bit deeper, and there are fancier, less well-known versions of range analysis. In particular, a technique called affine arithmetic, which is a different kind of range analysis, which is more complicated but more powerful than interval arithmetic. And I don't want to go into all the really low-level details of affine arithmetic, but the intuition you should have is that if interval arithmetic is like a 0th order method, and that is just kind of tracking constant bounds, affine arithmetic is like a 1st order method that tracks sort of linearizations of these error bounds, or these linearizations of uncertainty. So the actual data you track is, rather than just 2 values per scalar, so an upper and lower bound, you track sort of an expansion, a series of scalars. So you have this base x0, then a sequence of coefficients xi, and potentially a variable number of these coefficients. And these coefficients describe a linearization with respect to some error coefficients epsilon. So we imagine that these error coefficients range logically from -1 to 1. And then this expansion with a set of known coefficients x0 to xn gives the possible range of values that that scalar quantity could take over that region. This is important, though, because this change, it seems kind of weird when you talk about it like this. But what happens is that when you add 2 of these quantities together and you see that they have the same epsilon coefficient, it means you can allow the coefficients to cancel. And this cancellation property means that this affine arithmetic is exact under affine operation. So under addition, subtraction, multiplication by a constant, these bounds stay perfectly tight. And this is wonderful for neural networks because a whole lot of the computation happening in an MLP is exactly these affine linear layers of our network. And these pictures down at the bottom sort of give the intuitive picture. So rather than just tracking a Cartesian rectangle that bounds some quantity of interest, we're instead tracking a polytope that bounds the function we're interested in. Although, of course, the actual picture we need here is higher dimensional and a bit harder to imagine. But at the end of the day, this is still an automatic arithmetic procedure. We just turn the crank on a computational graph and we get out for any particular input bounds on the output. There are some more numerical decisions to make because this is a more complicated numerical method. In particular, we need to decide how many terms to keep in this expansion and exactly what policy to use when sort of adding and truncating terms. And a big part of the sort of scientific work that we did here was finding just the right variant of affine arithmetic that works well on these kinds of neural networks. But in the end, it works pretty great. And we get out an automatic computational procedure that gives fairly tight bounds on the outputs of our neural networks over query regions of interests with only a modest computational overhead. In particular, our techniques end up being 10x to 100x more expensive than just a single forward pass. So that certainly hurts. But on the other hand, we're able to analyze whole big chunks of space at once. So even if it's 100 times more expensive, it's still very productive in terms of the operations we want to do. So the takeaways here, I think that this is interesting. These techniques are really numerically fascinating, even if we don't care about particular applications in 3D. So this sort of recap of range analysis is that the idea of it is that given some function of interest and some query region you care about, it gives you bounds on the output. So it's like autodiff, but instead of computing derivatives, it computes bounds. And by the way, you might have heard of things like Lipschitz bounded neural networks or other techniques that we can use to put global bounds on our networks. Notice the thing that's happening here with range analysis is we're putting local bounds. So we're not computing some bound that tells us something over all of space or all possible inputs to our network. We're really only computing bounds with respect to the region we care about. And that's another reason we're able to get much tighter bounds for very general classes of networks. But these bounds are not necessarily tight. So we need to find just the right variant of range analysis, this thing called affine arithmetic, and still make some careful numerical choices with regards to the trade-offs between the tightness of the bounds and the computational cost. So both classically and in our case, this ends up being a secret sauce for a lot of numerical algorithms. It's very general, but there are some challenges still to using it. In particular, it depends on how the function is written algebraically, which is kind of crazy. We saw that with the identity example, and it's also not widely implemented in software. But pulling all of this together, what we get out is this range bound subroutine, which says, given some implicit neural function and some region of it that we're interested in, and in particular, we describe these regions as being k-dimensional boxes, not necessarily axis-aligned boxes in space. So in the case of arrays, we have a one-dimensional box of inputs that we care about, or we could also imagine analyzing little cubes in our case, which are three-dimensional boxes. Or this even generalizes to n-dimensional boxes over latent dimensions or something like that. And we implement this in a GPU space framework with a bunch of tricks for efficient vectorized implementation and so on. So what all of this does is it allows us to build geometric queries on top of this range analysis. And by the way, you might have noticed something interesting happening here is that even though I'm telling you about a new way to use neural networks for these problems, we're not introducing any new architectures. I'm not introducing any new loss functions. We're not presenting a new model for learning these kinds of tasks. Instead, what we're saying here is you hand me a neural network, you fitted a neural implicit function to some data with your favorite method for your favorite task, and we're giving you additional ways to analyze that function. So now we can roll through here a little bit quicker and see all of the queries that we can build on top of this basic range analysis operation. So the first one is this ray casting operation that I've talked about before. And ray casting is really important in graphics and vision because one of the most standard things we want to do is render images of our 3D objects. And rendering an image basically means taking a camera view and saying for each pixel in that camera view, let's shoot a ray out of that pixel and see where it hits the surface. So we need to cast millions and millions of these rays to form these images. And here, all of these blue shapes that I'm showing are implicit neural surfaces that I fitted to various data of input. These are all sort of in this overfit regime. And these are all from a random collection. I used a bunch of different loss functions. So here, this was fitted as an occupancy network. They use different network sizes. They use different activation functions and so on and so forth. So we're analyzing a very general collection of inputs here. So on the right is this first image where we're just forming an image of this neural implicit shape with this machinery. You can even take this a step farther and say, rather than casting each pixel ray individually, let's take a whole block of pixels, which are adjacent in image space, and put a little 3D frustum, a little prism around those pixels and analyze all of them at once. And if a single pass of range analysis tells me that that whole frustum does not contain the surface, then I can step all of those rays forward at once. So this is like a hierarchical spatial acceleration that we can do with this geometric operation. And sure enough, it gives much better scaling and some significant speed improvements to high resolution images. To give a quick sort of example of alternatives here, if you didn't have this machinery, the best you could do to cast rays against a general neural implicit surface would be to sample a whole bunch of points along the ray very densely and check when those the sign of the sample changes from positive to negative to detect when you've crossed the surface. But this is dangerous because if these samples are too far apart, you might miss your surface entirely. And on the left, that's exactly what happens. And we get these little holes in our rendering because our ray casting has missed the shape. In the middle, if we take small enough steps, this problem goes away, but it becomes incredibly expensive. And on the right is what happens when you do this using our method, and it ends up being both has guaranteed accuracy and it's even faster in the end. Here's a cool video that we can make with this technology. So this is not the main point of this project. I just think it's fun to generate these kinds of visualizations. So here we're looking at the training process as I overfit a neural network to a very small neural network to a single shape, which is a 3D model of a fox. And because we're able to render the corresponding function, even when it's a crazy randomly initialized function, we can actually visualize the whole fitting process. And it's kind of interesting to watch. I think you could learn something about training dynamics by sort of visualizing this data. But of course, we want to use this more generally for lots of applications. Another cool connection that this builds is that we can also analyze balls of space to test whether or not they contain the surface. And this turns out to be enough for a class of algorithms called Monte Carlo walk-on spheres PDE evaluation. So the setting here is we want to evaluate Poisson-like PDEs over the volume where the boundary conditions for the PDE are Dirichlet boundary conditions taken from the surface. And these are useful for all kinds of problems in engineering and graphics and vision. Because they just need this query of finding these empty balls to evaluate a random walk, we can run this algorithm essentially for free on a neural implicit shape using these queries. We can push this even farther by starting to build spatial hierarchies and acceleration structures over our shapes. And this is sort of the bread and butter of geometric algorithms in graphics and vision. So what we can do is we can construct a KD tree over our space, where each cell of the KD tree is classified as saying our implicit function is either strictly positive in that cell, strictly negative in that cell, or we don't know, and we recurse into two smaller cells. So on the right here, I'm showing a visualization of one of these KD trees that has been built again over a coarse visualization of this implicit model of a fox. So each of the little rectangles you're seeing, hopefully the video is not too bad, is a node of the KD tree. I've chopped it off at some certain depth, so we're not going all the way to the bottom of the KD tree, just to some intermediate depth. So the yellow nodes, the yellow rectangle boxes, are all classified as being certainly strictly outside our implicit function by range analysis. There are some other green boxes you can't see, which are strictly inside the shape. And then these purple boxes are the ones the nodes which were still not yet classified successfully as being strictly inside or outside. So we'd have to keep descending the KD tree until eventually we would bound them. One thing that I think is really interesting about this is you see these little lines, planes shooting off through space. And what these are, they're actually the elbows of the ReLUs in the first layer of the neural network. So because there's like this nonlinear elbow in the ReLU, you have to descend farther in the KD tree to bound the output of the function right around that ReLU. So you actually see this in the how far you have to refine the KD tree. So the algorithm still works. You keep descending. Eventually, these get classified, and you're good to go. I just think it's cool that you can see these things when you visualize the data. And once we have this KD tree, now we get access to all of the geometric algorithms that we build on top of KD trees. Really quickly, there's a lot more details on this in the paper, but just to give a call out to how we define correctness for these problems, it's tempting to define correctness by looking at the magnitude of the implicit function, but that's actually no good in this case, because when we have a randomly initialized function, its magnitude could be varying wildly all over the place, which means that a bound based on the magnitude of the function doesn't actually tell you anything about a geometric bound in space. So instead, we formalize this as guaranteed correctness for a surface which is a dilation or contraction by some small delta. And these deltas are incredibly tiny. They're like almost floating point epsilon. I think it's like 1e-4 for the examples I've been showing here, which is like 1/10 of a pixel in screen space. So in this sense, we get guaranteed, computational geometry style accuracy on these problems. Floating point analysis is really hard. We don't do anything special in this case. If you wanted, you could try carefully controlling the rounding modes in your floating point computation, but we don't go there at all. And in practice, everything seems to work out just fine. So to show a few more of these queries real quick, another common one is sampling points near a surface. So this shows up a lot evaluating loss functions, for instance, in geometric learning. You could just naively rejection sample, but instead, if we build this KD tree and only rejection sample from the nodes which might contain the surface, we get a 10x or more speed up once you're sampling enough to overcome the initial cost of building the tree. And here, this is not an approximation algorithm. We're getting the exact same output from the sampling procedure. This is just an acceleration that skips all the regions we don't care about while maintaining provable correctness. We can also do the same thing if we want to extract an explicit triangulation of the surface that corresponds to this neural implicit function. And here it's basically the exact same trick. We just only perform extraction on the nodes of the KD tree, which might contain the surface. And again, once you're working with large enough data to overcome the cost of building this KD tree, it gives you a 10x speed up or more. We can also come back to this question I motivated with a long time ago, which is given two implicit surfaces, how do we check if they intersect one another? So here we build this combined KD tree over both shapes, where we descend into each node of the KD tree only if both of the functions might be positive in that node. And eventually, either we get a certificate that the surfaces do not intersect, or we find a point which is strictly inside both surfaces, and thus we know a point where they do intersect. And then our teaser figure here is actually from doing these geometric closest point queries, which is to say, given some point sitting in 3D space, what is the nearest location on the implicit surface, on the level set of the neural network? And I think this is a particularly fun query because if you just, before having all this machinery, if you just handed me a neural network, I would have no idea how to find the nearest point on its level set. But it's pretty fundamental, and as you would expect, this is what KD trees are good for. We did not invent this. KD trees are for doing closest point queries, once we have a KD tree, then we can use it to evaluate these queries very easily. And then lastly, this is the example I showed at the very beginning, where we use many of these raycasting queries to solve a really simple inverse rendering problem, where we try to match some rendered views. Now, this doesn't hold a candle to the latest and greatest actual research projects on inverse rendering, because they use much more complex formulations on much more difficult data. But what this is a proof of concept showing that our geometric query is really useful for these kinds of operations. So now you can, and people are building fancier inverse rendering operations that just use our raycasting query as a way to interrogate the underlying neural network. So it's sort of a useful tool for all of these general operations. All right, we can wrap up here. So to recap, this whole project on range analysis of implicit surfaces. So again, the big idea was analyzing implicit neural networks using this numerical technique of range analysis, and doing so unlocks all kinds of geometric queries and hierarchy building on existing neural implicit representations. So we didn't invent a new network. We gave you a new way of analyzing the networks you already have. Some things we're still thinking about. One is to say that I mentioned an alternative solution here is to just approximately fit an SDF. The techniques that do this, and they work quite hard to make sure they have nice SDFs, they end up being faster than what we're doing here, because this is a more general sort of guaranteed method. Generality isn't free, you pay something for it. So it'll be interesting to see how these techniques kind of converge in the field. In this case, I mainly analyzed simple MLP-based architectures, or really just simple feed-forward MLPs with this range analysis. In principle, it applies to just about any neural network architecture you could write down, but we haven't really done it yet. And there's also some interesting questions to ask there about software systems and programming languages to sort of support these kind of numerical techniques more automatically. And then the last thing that's exciting is building all kinds of, this full stack of sort of graphics and vision on top of these queries. So I want to leave with a last question just to think about, and maybe if anyone has any thoughts in this space, I'd love to hear about it. I know that you all have, a huge amount of expertise across these subjects. So I think it's still kind of unknown what are the ubiquitous representations for 3D geometry and machine learning. It took us 30 years in computer graphics to settle on a small handful of representations, meshes and point clouds and voxels, and sort of know what their strengths and weaknesses. But we're still in the stage in learning right now where every week we have a new representation. So I think the big question are, what are the right representations? Is there just one, or are there sort of a handful of representations with various trade-offs? And how do we start settling on these as standard format so that we can start building up the stack of reusable tools and applications, rather than sort of inventing a new representation with every research paper? Because this is really necessary to help us build more cohesive frameworks and sort of move our whole field together forward into these techniques. So with that, I'll wrap up. My website link here is at the bottom. If you're interested in the paper, we have code up for this project and many others. And if you're interested in more of this, feel free to shoot me an email anytime. I'm always happy to chat with people about this kind of stuff. So thank you all for your time. And I think we have time for some questions here. I don't know.
We have time for some questions. So if you have questions, please ask. Any questions? Yeah.
In the raycasting experiment, what were steps? There was a term that said steps, and I'm not quite sure what.
Could you hear it, Nick? So in the raycasting experiment, what were the steps?
Oh, in the visualization I showed in the little figure.
Yes.
Let me pull it up here. Yeah, so this one. So here in this plot on the right.
Yes.
Yeah, so this raycasting is an iterative procedure where we march forward along the ray. We take these steps forward and forward and forward along the ray, and each time we evaluate the network, or really we analyze it with range analysis. So the quantity being plotted in the middle is the number of steps it took along the ray to eventually either converge very close to a point on the surface or diverge into space. So it's actually kind of cool. You see the regions on like the silhouette boundary of the shape are where it takes the most steps. And this is an interesting sort of common trend with these algorithms, that the silhouettes are the hard points because your ray just barely grazes past the surface. takes a bunch of tiny steps near the surface, and then eventually shoots off into the distance.
Yeah, go ahead.
Yeah, so quick question. When you went to the when you go into affine arithmetic to fix the linear arithmetic error bounds, the quantity n seems to be like really fundamental. Like it's I guess it's your dimension of the polytope you use. Is that something that you choose, or is that something that is sort of natural given the function?
Yeah, that's a great question. Yeah, so this n is kind of naively, if you do the most naive kind of affine arithmetic, what you do is every time you encounter a nonlinear function, you expand n by 1. So you start out with just whatever 0 of these terms or 1 of these terms, then you hit the first nonlinearity, now you have 2, another nonlinearity, now you have 3. So the length of your expansion is growing as you push through the computational graph. However, this sort of blows up the computational complexity in a deep graph of many computations. So instead, what you want to do is you want to compress it and condense terms. So you say these two terms are similar. I'm going to approximate them by condensing them down into one term. So now you have kind of this design decision in your numerical analysis, which is what is my policy for compressing these terms? How many am I going to keep? And when am I going to condense them together? And by the way, if you do this condensing right, you're not hurting correctness. You're just trading off slightly looser bounds for the case of less computation. So really concretely, I think in our case, we found it best to keep 8 terms always. So this expansion n was always 8 for us. And then whenever we hit some more non-linearities in the computational graph, we would condense down and keep only the 8 most significant terms. But we even have like a little study where we look at a collection of policies for this. And it turns out that in different settings for different algorithms, different policies are more numerically effective than others.
Thank you.
Nick, we have to wrap up because there will be a lecture here, so we don't have time for any more questions, unfortunately.
Okay.
So yeah, thanks again for amazing talk today. So I will create a meeting link for you around 1:30. Just join it and we will continue the second one-to-one meeting at 1:30. Yeah, thanks again for amazing talk.
Sounds good. Thank you, everyone.
See you.
Yeah.